So I think we stop right here. In this, I think we stop right here when we talk about regulation, right?
Yeah.
Have we talked about specific parts of the renal tubules yet? Like the proximal convoluted tubule, what does it do, that kind of stuff?
Yeah, we did that.
We did this too?
No, we didn't.
All right, so let's talk about proximal convoluted tubule first. Again, we do not use the term urine until it goes into your minor calyx. That fluid that we filtered and now it's running down your proximal convoluted tubule, then going through the loop of Henle, then up and through the distal convoluted tubule, and then into the collecting ducts. That fluid is called filtrate. It's not urine, it's called filtrate because we've already just filtered it. The results that we're going to see is due to diffusion, facilitated diffusion, active transport, symport, and osmosis. Now, the results of tubular absorption are due to all of these. The big driving force I want you to always keep in mind is water always follows solid movement. Unless we specify that we're blocking water, anytime water moves, water is moving because it's going to a higher solute concentration. So whenever we move salts, we will always have osmosis and water moves with it. Substances, so when you hear facilitated diffusion, regular diffusion, active transport, even symports, whenever we're moving any kind of solute, osmosis occurs. Substances transported are substances that are reabsorbed will then need to be transported from the interstitial fluid and into the peritubular capillaries. So what we need to do is get it away from the lumen. So this is a proximal convoluted tubule right here. This is the lumen. The lumen is where that filtrate that we have just filtered from blood enters. So think of our funnel. This is the opening to our funnel. As our funnel allows us to kind of open up right here, now that filtrate is going to course through our proximal convoluted tubule made out of simple cuboidal epithelium with lots of microvilli. What we need to do when we reabsorb is to get it through the cells, and we need to get it into the cell, out of the cell, on the opposite side. Once it's out of the cell, it's in the interstitial fluid space. It does us no good to keep it there all the time though. So once we get it into the interstitial fluid space, we need a blood vessel next to that, so then we can transport it into your bloodstream. That way, whatever we reabsorb and moves through the cells will be then reincorporated into your blood almost immediately. Perfect. That's what we want. Remember, we're going to filter almost 180 liters of fluid a day. 180. And only 1 to 2 liters of urine will be produced per day. So it's like a 99% filtration and reabsorption rate. And even things that we don't want right now, let's say salt, sodium chloride. Well, it's only recently that we had such a glut of salt. Before the last 100 years, salt was in very short supply. So much so that huge dynasties in China, huge dynasties in Africa would rise and fall because of the salt trade. So salt is incredibly important. And our body's system here is meant to reabsorb as much as possible. And as you reabsorb all that salt, your solute then increases into the interstitial space, moves in there, and then goes into the peritubular capillaries where your bloodstream is. Perfect, right? You want to move it from that filtrate through the cell and then eventually into the bloodstream. Once we have it enter the bloodstream, then we will have full reabsorption. Now, what gets absorbed where? So if you think about it, here they're taking a big look at and magnifying one specific cell of your proximal convoluted tubule. What you'll notice is on this side, that's where the filtrate flow is occurring. On that side, you're going to have sodium and chloride sodium and glucose, sodium and amino acids. Notice that in order for amino acids, glucose, and even chlorine to get absorbed and to move into the cells, it always has a little bit of sodium that triggers it. This is a symporter. Now, why does sodium want to go into the cell? Now, it's going to want to go in, but why? It wants to go in because of this. Another secondary active transport pump. A primary active transport pump is like when we're looking at the neurons and we talk about sodium being pumped out here, potassium being pumped in. Well, the sodium moved out here and the potassium pumped in, that's actively transported in a primary fashion. You're driving sodium movement. In secondary active transport, the sodium that's moved out only sets the environment. If I keep pumping sodium out, sodium inside the cell, very low. Now, sodium in our filtrate will be very high because sodium chloride and all salts are freely filtered. They get right through the barrier, right? The basement membrane, the filtration slits, they do not stop sodium from getting through. So what happens? The sodium goes through your filtrate into the proximal convoluted tubule, and because each of these cells, each of them have a lot of sodium potassium pumps on the opposite basal side, what happens is each of the cells are going to have a low sodium environment. That low sodium environment means sodium that's high in the filtrate wants to go into the cells. As it goes into the cells, it then brings chlorine along, glucose along, amino acids along. In other words, we need sodium. Even nowadays, we think about sodium as purely bad, right? Well, it's because we have too much of it now. But if we didn't have any, we'd have a hard time activating these pumps. So we have a hard time activating these symporters. They're not pumps, they're symporters. If you have a hard time activating the symporters, then you're going to have a hard time absorbing the glucose, the amino acids, and the sodium chloride from your filtrate. If that doesn't move in, then water isn't going to move in as well. So we need sodium to drive the reabsorption of glucose, amino acids, of sodium chloride even, and then with it, water. Why does water move? Because it's following all these solutes being moved. So if you stop everything because we are eating no sodium at all, what happens? Well, you don't have sodium inside the cell, you don't have sodium outside the cell. There's no movement of sodium because there's no sodium. Because there's no sodium, glucose doesn't get absorbed. Amino acids doesn't get reabsorbed. And water doesn't move along. You have a lot more urine output. Reabsorption will just stop. So we need the sodium to allow us to have all these reabsorptions. Pretty crazy, right? Because we always think of sodium being really bad. Well, it's really bad because we get so much of it. And a lot of it is almost insensible with that. We don't even taste it. You look at something like a Diet Coke. It doesn't have any sugar, but if you look, it's got sodium. Why? It makes it just a little bit more tasty, right? So let's take a look at the proximal convoluted tubule. There's something very important here. Number of carrier molecules are limited. There's only so much room for these symporters because there's only so much room that we see in the proximal convoluted tubule. It's only the very start. And what we're going to see is all small proteins, all glucose gets reabsorbed only in the proximal convoluted tubule. Once glucose goes past and goes into the descending limb here, once glucose goes into this narrow descending limb, there's no more glucose that can be reabsorbed anywhere else. Now, most of us have a low amount of glucose in our bloodstream. Because it's lower in the bloodstream, or normal in the bloodstream, whatever glucose is there gets freely filtered. Yes, we do see glucose in the filtrate. Most of us, though, don't see glucose in our urine. Why don't we see glucose in our urine? Simple. all the glucose that we have in our filtrate gets reabsorbed in the proximal convoluted tubule. In other words, the quantity of glucose is low enough that as that filtrate full with glucose goes through the proximal convoluted tubule, as that normal amount of glucose goes through, there's enough receptors, so then we can reabsorb all that glucose. And by the time that filtrate enters the thin descending limb, all the glucose that was found in the filtrate previously, all of it would be reabsorbed. Now, what happens if there's just too much, right? You have diabetes, and because you have diabetes, your blood sugar is elevated, maybe 2, or God forbid, if you have type 1 diabetes, 300-400 type of, right? 300-400 milligrams per deciliter of blood. That's a high blood sugar count. What happens is your blood glucose levels are so high that your filtrate levels are incredibly high as well. They mirror each other. So the higher the blood glucose, the higher the filtrate glucose. What occurs then? What occurs is as that filtrate courses through, there are not enough receptors to reabsorb all that glucose as that filtrate enters a descending limb. As it overwhelms all of these receptors, what happens? Some of the glucose stay in the filtrate. Some of it gets reabsorbed, but there's just too much to reabsorb. And what happens? The glucose goes through the proximal convoluted tubule and into the descending limb. When that happens, there are no more sodium glucose receptors found anywhere else. They're only found in the proximal convoluted tubule. When that glucose then goes through the descending limb, ascending limb, goes through the distal convoluted tubule, goes through the collecting duct. As it goes through all of those regions, there are no more sodium glucose cotransporters anywhere else. Because of that, the glucose is no longer reabsorbed. Whatever is found in the filtrate, that glucose will go through the collecting duct, go into the minor calyx, and now we have free glucose in our urine. We call that glycosuria. Now, should we, if we have normal blood sugar, have lots of glucose that overwhelms our ability to reabsorb? No. We should have enough sodium glucose transporters in our proximal convoluted tubule to reabsorb almost all of the glucose if you have normal to high normal blood glucose levels. If your blood glucose levels is about in the 200 range, that's too high, you overwhelm the sodium glucose cotransporters, you just don't have enough. Because of that, glucose stays in the filtrate all the way through. And now we have glycosuria. Do you guys know what they used to, how doctors used to diagnose diabetes in the old days? I don't know if I told you that story, right? So doctors in the old days, because there are no test strips for glucose in the 1500s, right? So how does a doctor diagnose diabetes? What they would do is dip their pinky into the urine and taste it in their tongue. If they can taste glucose, then you have diabetes. Now, God forbid you have very, very dull sensation of taste for sweetness, right? You'd be dipping your finger all over the place. It'd be kind of gross. But that is how they used to be able to diagnose it, is to actually stick their finger in there and then taste it and put it in their tongue to see if it has a sweet taste to it. Now, back in those days, there was not much we can do with people with type 1 diabetes. We didn't have insulin until the last 100 years, last 60 years about. So what else do we see with diabetes? Lots of urination. We call it polyuria. So there's polyuria and glycosuria found in diabetics. Glycosuria, lots and lots and lots of sugar. That's why we get the glyco, urea for urine. So what happens if you have a lot of sugar and glucose going through into the nephron loop, into the distal convoluted tubule. Well, what happens is you have a lot more sugar than you should, and it causes less fluid to be reabsorbed. Because if so much glucose in the filtrate as it flows through, it actually hinders that osmosis and water movement. What happens then? Less water moves in and less water gets reabsorbed. Because there's less water that's reabsorbed, there's more filtrate going all the way through. More filtrate means more urine. And that's why we see the polyuria as well as the glycosuria. The polyuria is caused by the glycosuria because of the increased presence of glucose. The solute levels should be pretty low as we go through. What we're going to see is it's higher than normal because there's so much glucose in the filtrate. Glucose that should not be there now is present at high levels. No longer makes it so that water no longer wants to move through again. As water is no longer reabsorbed at the same rate, there's more water going through your tubule system. You can't reabsorb at all because there's so much glucose there, holding that fluid in place. Now you have a combination of glycosuria and polyuria. Now, one thing we also see with diabetics is something called polydipsia. Polydipsia is increased drinking of water, right? And that kind of makes sense why you have increased drinking of water. It's because you have so much urine output that you lose so much water. And your body then has to compensate by having you drink more and more water. So those are the three conditions that people ask about with diabetes mellitus is polyuria, glycosuria, polydipsia. And they're all related to the fact that we did not and we are not able to reabsorb all that glucose through the collecting duct, the proximal convoluted tubule. Once it goes through into the collecting duct, there's no hope of reabsorbing it all. You're gonna have increased urine output, polyuria, increased amount of glucose in your urine stream, glycosuria. The combination of those two allows you to be very thirsty, so then you can replenish your water stores and you will have increased thirst, increased drinking, polydipsia. Now there's an important one. Filtrate volume reduced by 65% due to osmosis of water. And all right, so highlight this area right here. And those areas right there, filtrate volume reduced by 65% due to osmosis. And then 100% of glucose, 100% of the amino acids are reabsorbed in the proximal convoluted tubule. So amino acids, small peptides are reabsorbed only in the proximal convoluted tubule. 100% of glucose as well. They're only reabsorbed in the proximal convoluted tubule, making it incredibly important in nutrient reabsorption. Now, let's talk about the loop right here, the loop of Henle. So now we have that fluid, Now we have that fluid going through into the descending limb. The descending limb of the nephron loop or the loop of Henle. What we're going to see is descending limb and ascending limb have completely different functions. By the time that fluid enters that descending limb, that fluid should have no glucose, no amino acids. It should just be hopefully like very, like salt water. That's it. There should be only 35% of what was found at the very start. You've already reabsorbed 65% of that filtrate. So there's a little bit less flow going through. Now what we're going to see is on the descending limb, it's very permeable, especially the thin segment. That's what we're looking at here. The thin segment is going to be very permeable to water. And what we're going to see is water is going to move out on the descending limb. As water moves out on the descending limb, we stop and prevent sodium and salt reabsorption here. So what happens? As fluid moves through and you reabsorb it, it then enters the blood vessel that lies right next to it, right? Keep in mind, you have the blood vessel called the vasa recta. As the blood vessel have blood that moves up right here. So the blood's moving up the bloodstream, filtrate is moving down the descending limb. They're moving counter current from each other. So they're moving in opposite directions, counter current. In a second, we'll see why we use that language. So as the fluid in the filtrate moves downwards, down the descending limb, water moves out of this tubule system. It moves out of the thin loop. As water moves out, water then goes into the interstitial fluid and into the vasa recta. The vasa recta has blood moving going upwards. That's going to be important, right? So for right now, I just want you to think, there's a flow of fluid and blood in opposition, right? And the fluid and flow, right? The fluid and flow right here allows us to concentrate urine incredibly well. So I'm just gonna, for right now, discuss, and I want you to think, descending thin limb, water enters and goes and gets reabsorbed, right? Let me rephrase that. Water exits. Water exits the descending limb, and only water exits. We're gonna see in a second why water exits out, right? Because remember, I mentioned that water passively moves because of concentration gradient. So we know inherently then that as that filtrate moves downwards and water exits, it exits because there's something drawing that fluid out, right? Now what else happens? As that filtrate moves downwards, it keeps losing water. As it keeps losing water, the filtrate inside becomes more and more and more concentrated, meaning that the longer this loop, here there's a pretty short loop, right? But the longer the loop, the more water can exit out and get reabsorbed. Remember when I mentioned that desert animals, desert rats, kangaroos, camels, all have incredibly long nephron loops. That is for water reabsorption. That's why they're able to survive a month drinking very minimal amount of water, right? For us, it takes a few days, and if we don't get water, we would basically die from it, dehydration. So what we're gonna see is this. On the descending limb, as filtrate moves through, only water moves out of the descending limb. Keep in mind though, I want you to think, water moves out, but it's gonna move out for a reason. As water moves out on the descending limb, well, what happens if you lose water in any fluid? If you lose water, that filtrate becomes more and more concentrated, right? Because all we're doing is losing pure water at this point and becomes more and more concentrated. As the fluid becomes more and more concentrated, by the time we see that it makes a U-turn right here, right? By the time it makes a U-turn, the filtrate will have a concentration that's maybe 600 times greater than what we saw at the very start. Usually at the very start of the descending limb, the concentration of that filtrate is very similar to the concentration of our plasma, 300 milliosmoles of solutes per liter, right? By the time you make the U-turn, the filtrate now, which was at 300, is now, should now be up to 1800 milliosmoles of filtrate. We've concentrated 600%, meaning that water moves out. As it moves out, solutes stay in, and it becomes more and more concentrated. So descending limb, only pure water moves. Now, on the ascending limb, only salts are pumped out, right? So water moves out of the nephron in the descending limb. Volume of filtrate is then now reduced by another 15%. And it's just pure water being reabsorbed at this point, no salts. On the ascending limb, we see permeability to solutes. And we're going to start pumping salts out on the ascending limb. Remember, we started at 300 milligrams or milliosmoles of solutes per liter. By the time we're done with the nephron loop, so much water has leaked out that we concentrated the solute to 1,800 milliosmoles. Now we have very concentrated, very salty filtrate. As we move up, we're going to start pumping the salt out, right? So as we start pumping the salts and the solutes out on the ascending limb, the filtrate starts losing salt. As the filtrate moves up, it loses more salt. So at this point, you'll be at, instead of 1,800, 1,200. As the filtrate moves up, we keep pumping the salt out. Now it's at 900. Moving up, we keep even pumping more salt, 600. By the time we move up here and hit the distal convoluted tubule, we will be back to normal osmolarity, 300 milliosmoles. By the way, these salt pumps right here, these are the pumps right here that allows us to reabsorb a lot of the salt, right, that moves up the ascending limb. And these salt pumps are what we see that we're inhibiting in people that are on certain Lasix, water pills, like hydrochlorothiazide. Hydrochlorothiazide are called loop diuretics. Why are they called loop diuretics? Because it affects the nephron loop. What happens? How does it affect it? Loop diuretics block sodium channels here. It blocks it. As you block the sodium channels here, the sodium that we are going to reabsorb, a lot of it goes right into the bloodstream. As it enters the bloodstream, it goes right into the descending limb of the vasa recta. What happens if I keep moving that salt from the filtrate into the blood? Well, if I keep moving that salt from the filtrate to the bloodstream, the blood that goes downwards becomes more and more filled with filtrate, well, more and more filled with salt. So all the sodium, all the potassium, all the chlorine, I'm reabsorbing on the thin and the thick ascending limb. All that salt, a lot of it goes right into the blood vessel right here called the vasa recta. It goes into the descending limb of the vasa recta. As it goes into the descending limb of the vasa recta, it makes sense. The blood on the descending limb becomes more and more concentrated. So as we move blood out here, move solutes up here, we move it from the filtrate, reabsorb it. Some of it stays in the interstitial fluid, some of it goes into your bloodstream. So these two vessels should have very similar osmolarities, because whatever you're filtering out goes, a lot of it goes into the bloodstream. So if the blood kind of enters here, the blood is at 300 milliosmoles of solutes. Very similar to what the solutes are in the filtrate up here, right? As it comes down, it receives more and more salt from all these pumps. So as that blood comes down, it picks up more and more salt. The blood becomes more and more concentrated of salt. As it comes down here and makes the U-turn, the blood osmolarity will be identical to the osmolarity of filtrate. 1,800 milliosmoles of salt, 1,800 milliosmoles of salt. It should mirror each other, right? So why is this important? Remember, as the blood moves up, it's receiving water, right? Receiving pure water. Remember when I mentioned that there's a reason why water wants to move out in the first place. The water wants to move out because the interstitial fluid is so salty due to the action of the pumps on the ascending limb. Because the pumps on the ascending limb is so active, we pump out so much salt on the ascending limb, some of it stays in the interstitial fluid space. Some of it goes into your bloodstream, concentrating the bloodstream. So as the fluid goes up, the ascending limb of the loop, we pump out that salt. Some of the salt stays in the medulla. Some of the salt stays and concentrates the medulla. And what we're going to see is that this counter current mechanism allows us to reabsorb a lot of salt, and with it, a lot of water. Perfect. Again, there's a reason why the longer the limb, the more water that can move out. You can imagine this limb and the loop right here is very short. So if it's very short, very little water can exit out because it's just too short. If it's much longer, what happens? If it goes all the way down here and then makes a U-turn, what happens is lots more water can leak out because there's more space for it to leak out because there's a longer descending limb. At the same time, why does that fluid want to leak out in the first place? What's drawing all that water out on the descending limb? What's drawing that water out on the descending limb is what's happening on the ascending limb. On the ascending limb, we pump out salt and salt only. Some of that salt stays in the interstitial fluid. Some of it goes into the bloodstream, concentrating the blood that goes down our vasa recta. So then as that salt goes into the vasa recta, the salt causes the blood to become more and more concentrated. And as that blood becomes more concentrated, now as the blood comes up, all that water we reabsorb, where does it go? Right into the bloodstream. Perfect, right? What we're gonna see is that water that we reabsorb on the descending limb of the loop, that water comes out because of the salt pumps on the ascending limb. The salt pumps on the ascending limb allows us to concentrate the interstitial fluid space, the space between the vessels here, as well as allows us to have increased salt concentrations in our bloodstream. So then by the time that blood makes that U-turn, it has picked up all that salt that we have pumped out on the ascending loop. So then it's very concentrated full of salt. Now as that blood moves up through this U-turn, well, that blood is very salty. What's going to be attracted to salt? Water. So that water that we are actively, that's moving out here on the descending limb, it just doesn't just stay in an interstitial fluid space. We want it to go into your space, directly into your blood vessel then. Into space, into the blood vessels. Into space, into the blood vessels. Now as it enters your bloodstream, we now have reabsorbed that water. We have now incorporated into your blood. Perfect. We picked up salts before, now we picked up the water. By the time we are able to, that blood exits through the vasa recta here, that blood will have picked up a lot of salt and a lot of water. That's reabsorption right there. Now let's take a look again on the loop, and here are the salt pumps that we see in the ascending limb. The wall of the ascending limb is impermeable to water, so only salts are moved out. What happens, right? As the salt is moved out, the salt goes into the interstitial space first, concentrates the interstitial space, then the salt moves into your bloodstream, concentrating your bloodstream as well. So what we see is, we should see a nice equilibrium between the salt concentration in your filtrate, then that salt moves into the interstitial space, so we should have an equilibrium here, and then the salt moves into your blood vessel, the descending limb of the vasa recta, causing that area right here to also have similar solute levels. right? Now, I'm talking about what we call the counter current mechanism here. And I'll come back to it at the end of the chapter if you didn't get it. We call these channels the sodium, potassium, chlorine co-transporters. And you are able to reabsorb sodium and potassium chloride from your filtrate. Keep in mind that filtrate now is very concentrated because all that water had moved out on the descending limb. So that filtrate is going to be high in sodium, high in potassium, high in chlorine. And we're going to pump it all out. As we pump it, we're going to bring it into the cell, out of the cell. Again, right? This is another example where the sodium potassium pump acts as a secondary pump. All it does is it increases or decreases the sodium concentration. Now sodium wants to come in, sodium comes in, it brings a couple of friends with it, right? Then we pump it out on the other side, concentrating the interstitial space. Some of the salt then moves into the bloodstream, concentrating the bloodstream. They all will mirror each other. So if I look at if I would take a cut right here, if I take a look at this cut right here, right, we're gonna see the filtrate concentration should be about 350, interstitial fluid, 350, bloodstream, 350. As we move down more, if we look at here, right, the filtrate, well, it's just moving upwards right now. So it's still, now you're gonna have greater concentration of salts. By the time the filtrate moved up here, that salt concentration has been lowered from previous pumps. So here we're at the middle. We just started pumping the salt over here. So at this point, right, the filtrate concentration of salt is high. Could be 900 here. Then we're gonna pump that 900, all that salt move into the interstitial space. Now the interstitial space will be in equilibrium, 900 milliosmoles. And some of that salt goes into your bloodstream, 900 milliosmoles. So when we look at specific regions of the ascending limb, we compare it with the interstitial space surrounding that region. The interstitial space and the filtrate should have very similar salt concentrations. I'm giving you the number 900 here in the filtrate. So you're gonna pump that salt out to the interstitial space. So in the blue, the interstitial space around the nephron, this area, at this level, also should be at 900 milliosmoles. The blood that enters and then exits, that blood as it goes through will also then pick up a lot of salt. So the blood should also be at 900 milliosmoles. See that? That's equilibrium. Now, what we see is this. When we give somebody a loop diuretic, we block these pumps and these pumps, right? As we block these pumps, what happens? When we block the pumps on the ascending limb, we no longer concentrate that interstitial space. Why not? Well, the reason why the interstitial space and therefore the medulla is very concentrated full of salt is because the action of the ascending limbs found in all of our nephrons in our kidneys. So on the ascending limb of this kidney right here, right, we are blocking the salt pumps. What happens? Salt cannot move out. Because salt cannot move out, I can't concentrate the interstitial space here anymore. Because I can't concentrate the interstitial space, salt doesn't move into your bloodstream. I can't concentrate the vasa recta. Because I can't concentrate the vasa recta, when blood moves up, it's not concentrated. Water then, on the way down here, well, does water even want to move out? No, right? Why doesn't water move out then on the descending limb? It's because by blocking this pump, all of these pumps here, I can no longer concentrate any amount of salt in an interstitial space. Previously, when I wasn't on the loop diuretic, that salt I pumped out on the ascending limb concentrated everything in the surrounding environment. Because now that surrounding environment is so full of salts, water on the descending limb will move out, right? So the reason why water and only water will move out on the descending limb right here is because of how salty the interstitial space is next to it. Next to that will be in the medulla. So the more salty, the more water wants to move out. Now we've blocked it. Because we blocked the salt pumps, there is no salt. And the interstitial space is not salty at all anymore. Because it's no longer salty surrounding the tubule here, water now has no reason to move out of our descending limb, right? Here, water wanted to move out on the descending limb. It only moved out because the interstitial fluid was so salty. And why was that interstitial fluid space so salty? It's because on the ascending limb, we pumped out those salts. And those salts that we pump out on the ascending limb, some of it stays in the interstitial space, stays in our medulla. And because of it, that's what drove water to leave on the descending limb. So you have one part of the limb, right, the ascending limb, completely causing what's causing on the descending limb. So the ascending limb concentrates the medulla, and with it concentrates the interstitial space in the medulla. The longer the limb, the more we can concentrate. The greater the concentration surrounding the descending tubule, right? The greater concentration of salt, the more water wants to exit into the space because it's so attracted by that high solute concentration in the space. Now, what happens if there is no high solute concentration in the space? Well, what happens is water is no longer attracted by osmosis. Because no longer is water moving out by osmosis, we will then have more water going through unreabsorbed. When that happens, I have more water going through the tubules, more water going through the minor and major calyx, more water in the urine. Perfect. That's exactly what we want when we give somebody a Lasix or a loop diuretic. We want them to urinate out any excess water they might have in their body. So by blocking the receptors here, I decrease reabsorption of water on the descending limb. We completely change the physiology of the kidneys by giving you a loop diuretic. Kind of crazy, but it is pretty crazy how quick it works too, right? In a couple days of giving you hydrochlorothiazide, almost immediately, these sodium and chlorine pumps get blocked. Because they get blocked, we no longer have very concentrated interstitial space. Now keep in mind, interstitial space is just that space found between cells, right? Found between blood vessels and loop, right? The interstitial space is found deep in the medulla. The deeper in the medulla, the more salt that should be there. But if we block all these salt pumps, what happens? There's no salt in the space at all anymore. If there's no salt in the space at all, that space surrounds everything. Since there's no more salt surrounding everything, there's no reason for water to move out of your descending limb. And if it's no longer moved out of your tubule, it's no longer reabsorbed. It stays all the way through. As it stays all the way through, you urinate out any excess fluid. Perfect. Again, right? We'll come back to that near the end. So on the ascending limb, we pump out salt. By the time we hit the start of the distal convoluted tubule, it's going to be kind of crazy. At the end of the loop of Henle, inside the nephron, there is an osmolarity of 100 milliosmoles. Meaning, right? Meaning that At the very start right here, we were 1,800 milliosmoles per liter, right? At the very end, it's at 100. That's pretty efficient reabsorption of salt, isn't it? If we were at 1,800 at the very U-turn with the filtrate, and now as it comes up, we keep reabsorbing all that salt by those salt pumps. By the time the filtrate hits the distal, at that junction, we have reabsorbed 1,700 milliosmoles of salt. Amazing, right? As we reabsorb that 1,700 milliosmoles of salt, some stays in an interstitium, concentrating all that fluid space found everywhere here. Some goes into the bloodstream, down the vasa recta, concentrating the blood. As blood comes down, it picks up more and more salt. It becomes more salty. As it makes a U-turn, the amount of salt in the vasa recta right here is similar to the amount of salt at the U-turn of our nephron loop. So it's very salty. That blood, when it goes up its ascending limb. As that blood goes up its ascending limb, it's incredibly salty. Why is that important? Because it drives water movement. From the descending loop, that water is drawn to the high salt environment in the interstitial space. As that water goes into the interstitial space, you're adding water to a solution. What happens? You dilute that solution, all right? Because you start adding water to the interstitial space, that water starts to have an effect and dilute it. Well, now the blood that comes up is more concentrated, and water is then drawn from the fluid space into the bloodstream. So on one side of the vasa recta, we reabsorb salt. On the other side, we reabsorb pure water. Perfect. Almost an opposite of what we saw here. Right? Filtrate within the distal convoluted tubule is much more dilute than the fluid in the interstitial space. It shows just how effective solute reabsorption is on this ascending limb. And it also, and kind of, if you're ever confused about this, probably the easiest way to remember it is what happens on the ascending limb causes what happens on the descending limb. So as you kind of understand that concept, now we can fill in the gaps. Well, what happens on the ascending limb then? Well, what happens is we pump out salts. As we pump out salts, it increases the osmolarity of all this interstitial space. As the osmolarity increases in this whole area, what happens? As the filtrate goes down the descending limb, that filtrate is going to encounter spaces that are very salty. What happens? Water is drawn out because there's a solute gradient. Water goes down and through our descending loop. As it goes into the descending loop, then that water goes into blood. That blood, why does the water want to go from that fluid space into the bloodstream? It wants to go in there because of how salty the blood is now, right? And now that water goes from the descending loop into the space, goes from the space into the bloodstream. Perfect. That's just pure water. We already have all that salt. We can mix it together to form that plasma. Now, in the distal convoluted tubule and the collecting duct, right? Sorry, guys. All right, active. Okay, I thought I let him in. Jesus?
Yeah, he said he wasn't being, like, it was waiting for you to let him in.
Yeah, but I let him in, but I don't, tell him, if you have him, text him and tell him that, you know, I tried letting him in. I'll let him in now when he has a chance. All
Okay.
right. Sorry, Ashley.
No worries.
All right, active transport of sodium out of tubules on the basal surface. Now, important thing to know about a distal convoluted tubule and collecting duct is this. This is the only region where there's variable permeability. And it all depends on the blood volume. Meaning what? If you are very, very thirsty, right? If you're dehydrated, the distal convoluted tubule and the collecting duct becomes more active. If you have too much water in your blood because you've drinking so much, right? Then the opposite occurs. They become less active. So this is the area that is the most variable in terms of activity. The proximal convoluted tubule, always active, always reabsorbs 100% of your glucose, 100% of your amino acids, right? 65% of your total solutes and right fluid. The descending limb and the ascending loop always reabsorbs 15% of your fluid and a lot of your salt. This is an area that is going to be variable, and is variable based on how much of our water we have in our body, and therefore how much of our hormones that we'll see. Some of you might have heard of the hormones, antidiuretic hormone, aldosterone. Well, this is the area where both of these hormones work on. They both only activate cells of the distal convoluted tubule and the collecting duct. They don't work on any other cells. Right? Now, changes in concentration of nephron, of the solutes in the nephron. Now, we can increase the amount of urea. Some enters a glomerular filtrate and we filter it. As volume of filtrate decreases, concentration of urea increases. Walls of nephron, not very permeable to urea. Only 40% is passively reabsorbed, meaning that besides a little bit of salt, the salt's being pumped out on the ascending limb, you have a little bit of urea that's also reabsorbed, but not to the full extent. You don't reabsorb 100% of the urea. Again, we don't want to, right? Urea is our way to get rid of ammonia, NH3 and NH2. Because it's our way of getting rid of it, the last thing we want to do is to reabsorb all of it. Remember, urea can be toxic. We need to increase its output. The more we get rid of, the better. And what we're going to see is the more urine you produce, the more urea, right, we can get rid of. Now, if you don't produce any urine, then the problem becomes we are unable to get rid of urea. And it becomes very toxic very quickly. Tubular secretion. So one of the things that we do see, where's that picture before? Right here, right? We have filtration, creating the filtrate. Then we'll have reabsorption, reabsorption of water, reabsorption of salts. At the same time, we also see secretion. And most of what we will secrete are NH3 compounds, urea, right, ammonia. That way we can get rid of all of it. Again, that urea is very toxic. We need to get rid of it. Right. Secretion usually refers to movement of nitrogenous waste from the bloodstream into the tubules. It can be done actively or passively. Ammonia produced by epithelial cells in the nephron from deamination amino acids diffuses from those cells that make up your nephron into the lumen. That way we get rid of the ammonia. Hydrogen, potassium, penicillin, and PAH are also secreted into the nephron. Hydrogen and potassium. Now, there's a reason why our urine is slightly, it's not, it can be a little bit more than even slightly acidic, right? So what we're going to see is hydrogen, and the concentration of hydrogen is what makes something acidic. The more hydrogen ions, the more acidic it becomes. Hydrogen ions secreted into the filtrate by counter-transport in proximal convoluted tubule. So what we're going to see is wherever sodium goes, hydrogen goes in opposite direction, right? Kind of sucks. So if I pump out sodium or pump in sodium over here, it's actually out. Hydrogen always goes in opposition. See that? So for every sodium that I reabsorb, I need something else on the opposite side with the same charge to go in reverse. So if I'm bringing in sodium with its positive charge, I'm gonna take out hydrogen with its positive charge. As that hydrogen gets moved out into the filtrate becomes greater concentration of hydrogen, which makes it slightly more acidic, right? That's great because then we can get rid of acids in our bloodstream. It's bad because there's a limit to it, right? The last thing we want to do is urinate out something that has a pH of 1, right? You'll be burning your urethra completely. So what we want to do is make a limit to how concentrated our urine pH can be. Because if it becomes too concentrated, it will burn when we urinate. So what we sometimes do is buffer the urine. So then we don't have such high hydrogen concentrations in our urine. So then we don't have such acidic urine, even though we're trying to get rid of hydrogens from our body. So that's what we're talking about here with hydrogen secretion, right? Hydrogen secretion allows us to get rid of any excess hydrogens in our bloodstream. Remember, our blood is slightly basic, 7.4, right? So if it becomes, you know, a little bit less than 7.4, 7.1, 7, well, that's acidotic, right? We're closer towards acid levels then. Well, what we need to do is get rid of excess hydrogens from our bloodstream. This is how, right? We take the hydrogen from your bloodstream, move it into the filtrate. As we move it into the filtrate, right, the pH of your urine will start to drop because there's an inverse relationship between hydrogen and pH. As it starts to drop too much, we then need to buffer it right here. We'll talk about some other mechanisms we have to buffer it as well in just a few minutes. Potassium as well, right? Hydrogen and potassium always moves in opposition of sodium. You can remember that by the sodium-potassium pump. So anytime we have sodium movement in one direction, either potassium exits out or hydrogen exits out, right? You need to balance the positive charges. So if I'm bringing sodium and its positive charge in, I need to have something going out. Usually it's either potassium or hydrogen. Now, we're gonna see, there will be some hormones like aldosterone. Aldosterone increases sodium reabsorption. A lot of sodium gets reabsorbed. What happens when you reabsorb a lot of sodium? A little bit of water follows, right? Now, the problem becomes we reabsorb so much sodium that we lose a lot of potassium. If we lose a lot of potassium, the potassium goes into the filtrate, goes out as urine. Now we have low potassium in our bloodstream. If that's the case, we're going to see some massive effects in our heart. Right? Urine production in the proximal convoluted tubules. Right? So this is good just to highlight everything that happens. Right? In the proximal convoluted tubules, sodium and other substances are removed. Filtrate volume reduced by 65%. And there's a big one. 100% of glucose and amino acids are absorbed here and only here. On the descending limb, water passively exits. Filtrate volume reduced by another 15% as pure water is reabsorbed. In the ascending limb, we have sodium channels, sodium chloride potassium channels that are transported out of the filtrate into the interstitial fluid into the vasa recta, right? The vasa recta is a blood vessel that follows the loop of Henle. The vasa recta and the filtrate, the blood in the vasa recta and the filtrate in the loop always goes in opposition. So as that filtrate goes up the ascending limb of the loop, as the filtrate goes up, the blood from the vasa recta going down, is moving against each other, right? We're going to call it, and we're going to have a specific name. It's going to be called the counter current mechanism. Here in the ascending limb, only salt moves out, and a lot of salt moves out. Water remains in the tubule. In the distal convoluted tubule and the collecting duct, the most variable region for reabsorption of salt and water, ADH and aldosterone works in these regions. If you're dehydrated, a huge amount of ADH is released, a huge amount of aldosterone. Aldosterone increases your sodium channels, allowing you to reabsorb more sodium from your distal convoluted tubule and collecting duct. As you reabsorb more sodium, a little bit of water follows with by osmosis. That's different than antidiuretic hormone. Antidiuretic hormone actually allows us to place water channels into these cells. Those water channels are called aquaporins. And as the water channels are placed into these cells here, now we have more water, and only pure water that's reabsorbed through these cells, right? No salt has to be moved. Only water is then reabsorbed. Both aldosterone and ADH will be released when you are dehydrated. Because I've heard that by the time you're dehydrated, by the time you're thirsty, you're already dehydrated, right? Coaches tell you that all the time. Maybe your parents might have told you that. Well, what happens is that's actually usually true, right? By the time you get thirsty, there has been a response by the brain already, telling you that there's already decrease in blood volume. At the same time, aldosterone's already worked. So what happens? You reabsorb a lot more salt because you're dehydrated, and a little bit of water gets reabsorbed. Well, what happens if you reabsorb a lot more salt than water? Well, your bloodstream, right, throughout your body, the blood's plasma, its osmolarity starts to increase because we reabsorbed so much of that sodium and very little water went with it. Well, what's the only way we have of decreasing our blood osmolarity? Drinking pure water. So if you've ever been in a summer, right, working out, gardening, right, and you only have that thirst for pure water, somebody gives you, like a soda or Gatorade, and it just tastes like it's syrup, right? And it doesn't even appeal to you after the first drink. You just want pure water. Why? Is because drinking pure water allows us to just incorporate that pure water directly into the bloodstream. Since your blood osmolarity is already high, putting pure water into it, perfect. You can decrease the blood osmolarity. So drinking pure water is the only way to decrease your blood osmolarity at that point. Right. Again, when large volume of water is consumed, what we call volume overload, our kidneys does a great job getting rid of excess water and salts. It does a great job. There's almost no limit to how much it can get rid of, as long as you let yourself urinate. That's a big one. All right. Don't ask me why people don't let themselves urinate, but I've heard of, for the most part, women, right, holding the urine because they don't want to get up if they're asleep. Get up, go urinate. All right. If you drink a lot of water, that's the only way we have of getting rid of that excess. Now, the problem becomes this. When we don't have enough water is when our kidneys are not as good. It does a great job getting rid of excess, but it cannot make new water. So when there's not enough water, the only way you can increase your water volume is to drink more. All of these mechanisms, right, where you're already dehydrated and now you're producing less and less urine, all those mechanisms are there to make sure that we don't lose too much more water. It's not there to increase water volume in our body. The only thing that can do that is drinking. Right? Mechanisms that create urine of variable concentration, maintenance of high concentration of solids in the medulla. So concentrating the medulla, obviously if you concentrate the medulla, as the filtrate goes down the descending loop, water exits because the medulla is in the interstitial fluid. And because the interstitial fluid is so concentrated, water will then leave on the descending limb. The countercurrent functions of the loop, and then ADH and aldosterone, and even another one called ANH, right? ANH, atrial natriuretic hormone, is the complete opposite of aldosterone. ANH is only released when you have increased blood volume, and it's released from your right atrium. So you're drinking too much, right? And you're drinking too much after a whole bag of potato chips, one of those big bags. And now you've had, a big bag of potato chips and 2 bottles of water right in a row. At that point, that water and the salt goes into your bloodstream, making the blood a little bit heavier, and ANH is released. ANH then will be the opposite of aldosterone. Instead of reabsorbing sodium and a little bit of water follows, now you're stopping sodium reabsorption in the distal convoluted tubule and the collecting duct. We stop all sodium reabsorption there. So then sodium is then increased in our filtrate, drawing more water towards the filtrate. So then you can urinate out that excess volume. Right. Let's take a little break, and then we'll finish this up. And then we will start with chapter 27.
I have a quick question,
Yes, Ashley.
or 2 actually. So I emailed you, but I noticed the test for 24 and 25. It didn't have a password for us.
Yeah, I saw
tried-
that.